Okay, hello everyone. Welcome to this CSM 61B Midterm 2 review session. Oh yeah. One second. Okay, yeah. So a bit of a disclaimer about, so today we're going to be covering a lot of topics. A disclaimer, CSM is not officially is not directly affiliated with core staff, so these slides may not be 100% comprehensive of what you're going to see on your midterm. The review session will be recorded and the link will be posted on the midterm 2 main post on Ed. And then the slides will also be posted in the midterm 2 main post on Ed after the review session so that you guys can take a look at the slides in your own time. We have a lot of topics we're going to go over. So we're very excited to do this. So yeah, each bullet point, each topic will take to around 15 to 18 minutes. So without further ado, let's get started.
Great. Dynamic method selection. Okay, so let's get into why Java is weird, right? So as we know, if you want to run a Java program, you have to do like two commands. The first one, you compile it down to some random code, and then you actually execute it. So because of this, Java has this weird mechanism when you're working with objects whose dynamic and static types are mismatching. You have to use the dynamic method selection process to determine which method will end up being executed. So first, well, I'll just go over like the process for DMS. During compilation time, the compiler would record the method signature of like the method that fits from the object static class. So a method signature is basically just a method name plus the type of the input parameter. So public void yellow vented in possible yellow. So yellow vented in possible yellow is the
sorry about that.
The method signature. All right, move on. So during runtime, the runtime system would show the slides.
I'm so sorry about this.
What happened?
I need to charge my laptop.
So, so during runtime, the runtime system would actually go into the object's dynamic class and try to find the method that matches the signature exactly. I hope people don't do this in slides.
No, they can't.
They cannot.
Okay, give it a minute and.
Okay.
Okay, yeah, 1 second. Really sorry about this, guys.
What's up? Okay, looks like we are back. And while we finish loading
this is not M1.
Oh,
genius.
Okay. That is great. Okay. We're fixed with that. So compilation type, the compiler records the method signature, which includes the method name and the input type. During runtime, Java will look for the same method signature in the object's dynamic class. And then if the runtime system finds the exact signature, it would execute the newly found method. Otherwise, it would execute the method found in the static class, no matter what. So just a note, sometimes like a dynamic method may seem like it fits the input better, but as long as the method signature is different, it will not be executed. So let's take a look at this first problem. On the top right corner, we have like the object map. We have a fingerprint, a key, a skeleton key, standard box, and a bio box. So in this case, I'll just walk through like the first one. So we have SPVB, which is a standard box statically, and a bio box dynamically. You call that object on unlock, which takes in a key K. So during compile time, it would not clicking. During compile time, it would go into standard box and try to look for the unlock method. It's going to see one, and it's the UK method, right? So the compiler would lock that method. Okay. It's not doing it. So during compile time, it's going to find UK, and then during runtime, we'll go into BioBox and try to look for this exact method public, unlock TK, and it will fail to find it, which means the result is that the runtime system will execute UK from standardbox. Okay, make sense? Keywords. Gotcha. So now we have these three problems. Maybe let's take like a few minutes to try them out. Oops. All right, let's go over these together. So the first line, it's doing that again. The first line, sp.unlock sk. Since the dynamic and static type for sp is the same, they're both standard boxes, it would work kind of as expected. During compile time, we'll go into standard box. It's going to find UK method, and then it's going to record it down. During runtime, the runtime system goes back into standard box and executes UK. For the second one, SBBB, the compiler would also find UK from standard box. And during runtime, the runtime system will go into BioBox and fails to find the same method signature. So it would still run UK. Finally, for Q3, BioBox to unlock SK. So in this case, static and dynamic types are the same. So the compiler would find USK in BioBox, and during runtime will run USK. Okay. If we don't have any questions, we can move on to iterators. Yes, we have a question. What is I see. That would be because skeleton key is a subclass of key. Okay. Right? Yeah. So the UK method would still be able to take in a standard key. Cool. Okay. Iterators.
Oh, cool. I didn't know that was going to look like that in the back end. Anyways, for iterators, let's jump in. Cool. So let me first talk about the motivation of a for each loop. So basically, if you look on the left, this is what a for each loop looks like. So you have for each integer x inside of a potential iterable. This one's called iterable b. You're going to print out x, right? So this is a pretty standard format, but I'm going to talk about like what it means technically. So basically, an iterable is something that you can iterate through, right? And then in this case, in each iteration, we're going to like go through or like take out an element. This time it's like an integer called x, and then we're going to act on that element. So in this case, we just continue it out. Okay, and then what this like transforms to, so what Java does like behind the scenes without the abstraction barrier, you're going to create an iterator for the iterable. And then what you're going to do is this iterator has like two capacities. One is calling the has next method, and then the other one is the next method. So now your for each loop is going to look like this. So while iterator B has next, we're going to print out iterator B dot next. And something like important to note about this, and also something like dangerous about iterators, is it only moves in one direction. It only moves forward. So for example, like once the element iterator dot next has been called, or once the iteration has passed, you can't go back to it. Okay, so now that like we kind of like went through what it would look like in real time, this is like what it looks like organized in the back end. So you have an iterable class, which basically like creates the iterator, right? And then you have the iterator class, which has the has next and next methods. And this is specifically what they do and what they look like. Cool. So in more detail, both of these classes, the iterable and the iterator classes, are interfaces, meaning you'd be creating your own classes and implementing them. Implementing these classes, if that made sense. And then for each interface, you have a type. And this type is going to be like what the elements in the iterable are going to be, right? So like, for example, you can have a generic type T, but then in our example case, these types were ints. And then to recap, iterables are what you traverse through. And then an iterator is the thing that traverses through the iterable. Okay, let's look at a problem. So I'm going to give you guys 2 minutes to just like look through this setup and think about how you're going to like, number one, like visualize it potentially, and then like the steps that you are going to take to approach it. Okay, so like as some like general pointers, what you see here is an array, so an integer array. So like this is going to be your iterable, right? You're going to be going through this array and like accounting for the details within this array. So what this is an array of voter counts. So every single index is going to be a candidate, and then the value inside of that index is going to be the number of votes for that candidate. And then you're going to define an iterator called vote iterator that like basically prints out all the votes for a candidate. So like, for example, for this one, when voter 1 has, for example, 2 votes, you're going to be printing out 1, 1. Okay. So the first thing that I like to do is like visualize everything. So this is like a 2D kind of version of what's going on. You have the array that's length, in this case, like 6. So it goes through 0 all the way up to array length -1. Right, and this x-axis is basically what each candidate is. So each index is a candidate. And then you go into like the y-axis, which is the actual votes themselves. So we have like the number of votes, right? Like displayed for each candidate. And like potentially we can like see into the future and like think that like there's probably a pointer called candidate that points to candidates, and then another pointer called num votes that points to the votes. Right? Because for each candidate, you have to document, or like you have to keep track of which vote you are on. Okay. So this is what the code looks like. You're like given the class, and then you're given a skeleton for, let's start with the has next method. So take a second to just like absorb this. And so like if you want to like hint for like how to think about this, you see that you have like two chunks going on. So usually when there are two parts, that means there's two cases to consider. And then you also see that like there's no space where you get to edit the instance variables, right? So like you're basically going to be like checking for situations, but you won't be able to touch anything. Is that enough time for everyone? Okay, cool. Yeah, but like basically in the class definition, we kind of expected this to go on. So like your array, your integer array is going to be called votes, I think. And then you're going to have two like indices that keep track of the like 2D like system that you're going to be like documenting. Right? The first one is candidate like this way, and then the second was num votes this way. Okay. And then in your constructor, it's pretty standard. You're going to take in the integer array, and then you're going to set the indices to 0. So you're going to start at the very corner. Okay. So there's like two like parts going on, right? So the first one, I'll just like tell you guys is like what's going on when you're at a specified candidate, or like when you're not going to be moving on. So let's say that we've moved on to candidate 1, and we're at like 1, 0. So like candidate equals 1 and num vote equals 0. So like what would be going on here? Like what would we need to check? Okay, so in this situation, we're checking whether or not we have like, we're like done with the candidate, right? Does that make sense? Okay, so basically, the code for this would be if num vote is less than votes indexed by the candidate, right? Because all you're checking is that in the current candidate that I'm in, is there enough, are there any like votes left over? Like, are there any next votes, right? Cool. And then in your second case, it's actually like really interesting because you notice that there's some empty arrays. So you wouldn't, not empty arrays, empty like candidates who have 0 votes, and you'd actually want to like skip over these, right? So what your for loop is doing is like that's why there's like the greater than 0 thing. Like it's like searching through the rest of the candidates and checking that there even is one vote that exists. So then your for loop would be like int I is going to start at candidate plus I, And then you're going to go until votes.length. So you're going to like search from after the candidate all the way to the end. And then, yes. Oh, shit. Yeah, that's the answer. And then, if there are votes that's greater than 0, then you're going to return true. Does that make sense? Can I get a nod? Okay, awesome. Oh, yes. Sorry, why candidate is oh. Because we want to start from like, oh, sorry, I said but you start from the candidate after, and then you go to the end of the array. Because like right now you're done with your first candidate. Because like the first if statement has passed, right? So now you're like, okay, starting from the next candidate all the way to the end, are there any more candidates with votes? Awesome. Yeah. If you saw the answer for the next one, pretend like you didn't. Okay, so then this is like the second method, right? You have a has next method, and then you have a next method. So how would you implement the next method? So in this one, like you'd actually be like changing the variables, right? Okay, I'll give you like a minute to look at that. So in this one, you kind of also have two cases. You have like the if thingy, and then you have like that doesn't happen, then something else happens, and then you're going to return something. So I guess like the place that you usually like start at is like you try to like finish the simplest stuff first, which is like, for example, the return statement, right? So like we're returning an int, and then according to the spec, I don't know what it's called, we'd be returning like what candidate that is. So what would you be returning? Candidate. And then yeah, I'll just show you. Why not? And then so you have like another section that's like that's like incrementing, or not incrementing, that's like repurposing num votes to 0. So like in what case would you be doing this? It would be when you're like going on to a next candidate, right? So then basically what this if statement is doing is it's just like once you're at the end of a candidate, you want to move to the next candidate. So like there's like kind of two steps in this. I mean, like first of all, there's like the case, which is like checking that like num vote is at like the peak of the votes, or like that you've met the number of votes that the candidate has. But then there's like two things you have to do. You have to reset the instance variables that you have. Right. So for candidate, you'd be incrementing it by 1. And num vote, you'd be setting it back to 0. In this case, it's already given. But this is how you would like think through to make sure you've like compensated for everything, or if you accounted for everything. And then the other case is like you're still at your candidate, like they still have more votes because they're awesome, and then you increment num votes by 1, and then you return the candidate. Okay, any questions? Okay, cool. Yay. And then okay, so this looks like a lot, but it's not. This is actually from the answer key from your past CSM worksheet, the iterators question. But what I wanted to like say, especially in cases where you have to like write the iterator, like the whole entire iterator process yourself, is like it's not as daunting as you think it is. Typically, if you're like, okay, this is the case where you're iterating, where your iterable is like one thing, like one array or something, it follows this process. Okay, so the first thing is like, obviously when you declare and instantiate all your instance variables, usually you'd start at 0, right? So that'd be like, yeah, instance variables and constructors, you set everything up. And then after that, you have the has next method and then the next method. So your has next method is kind of just like checking if there's something else, or like checking if there's another availability in the array to be in the iterable to be like sent out, I guess. So like typically like you'd have certain conditions you need to satisfy in order for there to like exist another element. So like this would be, for example, like a condition, or you've literally reached the end of the iterable. And then if this happens, you increment accordingly to your proper position, and then you return whether or not the index is still less than the length of the iterable. And then the other one is like the next method. And like this wasn't in the example before, but sometimes it's really cool because the next method actually implements the has next method and it makes your code a lot simpler. So right, for example, in this case, right, it'd be like, if you have a next thing, then give me the next thing, right? It like logically makes sense. So yeah, so I just wanted to like highlight that you can treat the has next method as a helper method and like reuse it. So like basically it'd look like if has next, you would increment accordingly and then return the value, right? And then like, for example, if this doesn't happen, like we know that like at the end of an iterator, it just returns an exception. Yeah, so this is a general format. Cool. Any questions about iterators in general? Okay, cool. We can move on to asymptotics.
There's a chat question. Does the has next method need a return false statement? The vote one does not.
Okay. Oh, that's a good point.
I think,
Yeah, you should.
I will say this though, if it doesn't, if it doesn't, okay, so like for elegance, obviously you want to return false, but in this case, if it doesn't return anything, it will probably be null, right? And then the has next will technically return false. Is that correct?
is null false about it?
I think so. No. Either way, let's just remember to implement return false. Yeah, always.
Slight errata.
Yeah, okay.
I guess.
All right, so now we're moving on to asymptotics. Yeah, so with asymptotics, we have three common notations, but in general, you should remember a few guiding principles about asymptotics. The first one is we should always be ignoring constants. So n and 2n, they're both O omega theta of n to us. And we care about scalable cases. So something that works for a small case might not be accurate for the overall function. So this is like, you can't just say, the best case for this function is when the array is empty or like when the input is 0, because this isn't exactly what asymptotics mean. And the three common notations we use are O of n, which means our function is upper bounded by f of n. So this is like our function takes at most some multiple of f of n steps. We use omega of n, meaning our function is lower bounded by f of n. So we say that this means our function takes at least some constant multiple of f of n steps. And then we have theta of f of n, which means that our function is upper and lower bounded by two multiples of n. So the way I like to think about this is, if we say that something is theta of f of n, then it means that this function is the same shape as f of n. So like x squared is generally like bending upward. So that's like the same shape as something that would be theta of n squared, and so on. And here are some tips and tricks that we're going to put into practice. I'm going to leave this up for a second. Feel free to take a picture, screenshot, etc. I will say I like most of these have come from my past cheat sheets. General tips, these might not always work, but these all give you good starting places. If you see some for loop that's like, for in I equals 0, I less than n, and you're incrementing I once at each step, this adds a power of n to the asymptotic. If you see something like, for in I equals 0, I is less than n, and I gets multiplied by 2, starting from, oh, that should say for I equals 1. This adds O infinity, which is my bad.
If you see for I equals 1, I less than n, I multiplied by 2, or I equals n and I is greater than 1, I divided by 2, this adds a factor of log n. And if you see recursive calls, you should always think about some sort of tree structure to your code. And we'll be seeing this tree structure of our calls and our time complexity in one of the up and coming examples. So we'll see that soon. And this is a general hierarchy of time complexities. So you should always keep in mind that constant time is faster than logarithmic time, is faster than linear time, is faster than n log n time, which is faster than any polynomial, which is faster than any exponential, which is faster than n factorial. And these are two common sums that you'll see in analyzing runtimes. So if you have 1 plus 2 plus 3 and so on, all the way up to n, then you know your function is O of n squared, or at least whatever loop created this pattern is n squared. And then if you have the sum of like 1 plus 2 plus 4 doubling until you get to n, then this sum is 2 to the log n plus 1 minus 1, which ends up canceling the 2 and the log, and we get O of n. So, and then we also have some tips and tricks part 2. Does anybody want to spend any more time here, copying it, taking a screenshot, etc.? All right, I'll take that as good to move on. And tips and tricks part 2, if you see this pattern for in I equals 0, I is less than n, and then the inner loop loops up until I, then this is exactly the same pattern as we saw on the last slide, which is 1 plus 2 plus 3 and so on, which gives us an O of n squared. And if there are no if statements, you can usually think about your code as having an exact theta bound. And then also one last tip and trick is if you have some runtime, say theta of n, then you also have your function being omega of everything faster than n and including n. And you also have the function being O of everything slower than n. So for example, right here, this chain says if you have theta of n, then it's also omega of 1, omega of log, omega of n, as well as O of n log n, O of n squared, and so on. And yeah, so now that we've seen some of these tips and tricks, does anybody want some more time here, or can we move on to example problems? Cool. So let's move on to the first problem here, which is 2 of n. This actually takes one. All right. So I'll give you guys just a few minutes to think about this, and then we'll discuss the general structure and how to apply some of the tips and tricks we saw to this problem. Oh no. Oh no. Oh no. Fine. I think I fixed it. Yeah, oh no. I tried to move it so that if I write on the board, the people on Zoom can still see. Yeah. Don't worry about it. This is on assumption. Oh boy. Okay. I'll fix this. All right, so I guess we can get started with this unless anybody wants a touch more time. All right, so I'll put the steps up up here, but we can also look on the board over here. So we have this print call, and we assume that print calls take constant time. So this inner print call is O of 1. And then applying our tips and tricks, we see this pattern for int j equals 0, j is less than n, j plus plus. So this means that it runs this inside code n times, and it adds a power of n. So this entire block here takes O of n times 1, which equals O of n. And then lastly, we see this identical pattern repeated again for int I equals 0, I less than n, I plus plus. So this adds yet another power of n. So our overall runtime for here is O of n times n, which equals O of n squared. And of course, since there are no if statements in here, we can also say that this is a theta bound. So everything in here is theta bounded by n squared. Oh, I copied my own question wrong. That's embarrassing. I am so sorry about that. Okay, so let's actually look at the solution and do this properly. So the print statement is still theta of 1, and this is a j times equals 2, which is in fact a pattern that does not add a factor of n, but adds a factor of theta of log n. So we have theta of log n for this for loop involving j, and then this for loop involving I still adds a factor of n. So our overall runtime is n log n and not n squared. All right. Does anybody have any questions? All right. So yeah, let's move on to the next example problem, which is this function r of intent. And this is a recursive function, so drawing a tree structure for how the recursion lays out, and how much work is done at each layer, how many layers there are in total, etc., might be a good tip to help you solve this problem. All right, I guess we can get started thinking about this problem. So let me tab over to the solutions and let me fix whatever happened to the actual problem. Hold on. I think the wrong problem got shown. So let me fix this. All right. Oh. All right, we'll take a second for it to come back. All right, so we have this function bar taking in n. And this bar function, let's investigate the runtime starting from the inside out and seeing what happens. So once again, we have a print statement that runs in theta of 1. And we have this for loop pattern for int I equals 0, I less than n, I plus plus. So just like we've seen, this adds a multiple of n to our runtime. So now we have theta of n. And now we know that this function, before it does any recursive, it does theta of n work. So now let's see how the recursive calls factor into this. At the very beginning, we have one node and it does n work, right? And then after this, it calls itself twice, doing n over 2 work each time. And over here, we have n over 2, n over 2. And then this continues on with n over 4. And if we notice the amount of work at each layer, this sums to n work on the first layer, n work on the second layer, n work on the third layer, and so on until we get to the bottom of the tree, which I forgot to put in the problem. All right. So I'm sorry for the second mistake, but there's a base case here, and if it's n equals 1, just return. So this makes the bottom of our tree 1, 1, 1, 1, 1, dot, 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 n times. Or rather 2 to the log n times. And there are log n layers in total. Yeah. Does anybody want a clarification on why there are log n layers? Cool. So given that we have n work at each layer and log n work at log n layers, then we can just directly multiply the work and the number of layers to get our overall runtime of theta of n log n. All right, so these last two problems kind of gave you some sense of how to use them. So let's see how we can apply these tips and tricks to an actual exam problem. So this next problem is from the spring 22 final, and credit goes to Paul Hilfiger for this question. And yeah, he asked to analyze the runtime of the following code, assuming that P takes constant time, and all the linked list functions take time as expected of linked. Oh, sorry, question in the back. Oh, yeah, let me go back. Mhm. Sure. All right. So the question was, what happens if we have 3 calls to n over 2? So let's find some room here to draw out this tree. So we have n here, and then if we have 3 calls, we split into 3 layers of n over 2. And then each one of these splits into 3 calls of n over 4. So now let's count the amount of work that's done at each layer. So this layer has n work. This layer has 3 over 2 times n work. This layer has 9 over 4 times n work, and so on. So we get this interesting pattern where we have n plus 3/2n plus 3/2 squared n, and so on. So for this one, you would, So this pattern is something that you'll learn more about in other classes, such as CS 170, but in 61B, you can kind of think of this as a geometric series. And the sum of this series is I remember calculus to remember the sum of this series. Does anybody remember off the top of their head the formula for the sum of a geometric series? I think it's one over 1 minus 3/2 to the -1. All right. Right. This is a diverging sequence, but if it's finite, yeah. If it's finite, I think this goes to something like n squared with master theorem, but I don't think you would actually encounter something like this in CS 61B, but you could draw the tree like this, notice it's a geometric series, and try to sum it up with the geometric series. If you look at these slides after the midterm review section and they're posted on Ed, I will go and add a footnote to these slides with the formula for a geometric series and a worked out example of this question, because it likely won't show up, but it's an interesting question. All right. All right. And then this problem appeared on the spring 22 final from Paul Hilfiger. And yeah, I'll give you all a few minutes to figure out this problem. Oh, yeah, let me try to not kill the projector by doing this. Right, you're just gonna just unplug it for now?
Yeah, you can. All right. And everybody. And screwed it.
I murdered the projector again.
It's okay.
We're back. All right, so I'm going to go ahead and talk about this problem. So let's pull up the solution here. And yeah, so I guess one thing that we're going to try a little bit differently for this solution is looking at both of these for loops at once and seeing what they do. So notice how J starts from K and goes to N. So this means that this inner for loop runs N minus K times, or rather, if we see that K gets incremented by 1 at the end of each iteration of this loop, it runs N times, then N minus 1 times, then N minus 2 times, and so on until it only runs once. And this pattern should be reminiscent of one of the tips earlier, where this for loop runs whatever is inside of it, N squared, O of N squared times, or theta of N squared times. So we know these two for loops account for at least theta of N squared. So now we have to ask ourselves, what about the code that's getting run in the middle? Well, P takes constant time, but what about L.get? We have to remember that in a linked list, getting an item takes linear time, right? Because if a linked list is like this, then you have to go through every single item until you get to what you're trying to get out, which means that this line of code in the middle takes theta of N. And since we have this nesting of loops, we can just multiply again, and our overall runtime is theta of N cubed. All right. That's the last problem on asymptotics. Does anyone have any more questions? All right. If there are no more questions, I'll let the next mentor come up and present.
What are we sharing slides with? What are we sharing the slides with?
Just use the-
Yes.
And
Oh my gosh.
uh-oh. Yeah, give it 1 minute.
Yeah. So now we're gonna go over disjoint sets. So disjoint sets are a data structure that consists of a bunch of disjoint sets, and disjoint means that two sets are disjoint if they have no common elements, and a connected component is that for each item, the set of all items that are connected to that item. And this is useful for dynamic connectivity, percolation theory, and implementation of algorithms such as Kruskal's. Yeah, so every disjoint set has two functions, the connect method and the isConnected method.
The connect method creates a union of two sets into one big set, and the is connected is that given two random elements, check whether they belong to the same set. So if we run an example, connecting A and B, connect BC, and then connect CA. And note that for most implementation of disjoint sets, you don't need to connect C and A because they're already part of the same set. And then we connect BD and F and FG. And now when we call is connected on AB, we're just checking, are they connected? And this would return true. Connect CD, also connected in the same set, so true. And then if we ask connected EG, true. And then if we ask connected AE, this is false because they're not in the same set. So quick find stores connected components as set IDs, and it is connected method takes constant time, and the quick find is not ideal because connecting two sets is slow and impractical. I would just suggest putting like the runtimes on your cheat sheet for this. And then for quick union, it stores connected components as parent IDs by assigning each item as parents. And this results in like a tree-like shape. And connecting two sets would be equivalent of setting the root node of one set as a child node to the other root. And the downside is that the tree can get really tall and potentially even worse performance than quick find. And the worst performance tree would be like a spindly tree. So an example for quick union, this is from lectures. So if we called quick union on 5.2, we would be connecting root 5 to 2, turns 3, and then call 5 root on 2, which returns 0, and then set the root of 5 to the root of 2. And the runtime would be linear. And so that is connected method. Okay, so weighted quick union is just an improvement upon quick union that ensures that connecting two trees creates a new tree with the smallest possible height. So the basic rule for this is that we're always connecting the smaller tree to the larger tree. And so is this a solution? I'm going to skip that slide. So just take 3 minutes to, or not 3 minutes, just take a minute to think about like the worst case scenario that would cause like the height of a tree to increase. So basically the unioning a set with the same number of nodes doubles the nodes to add 1 to the height, which becomes log n. And then for weighted quick union with passive compression, the goal is to improve upon weighted quick union and make the average runtimes of connect A and B and is connected even faster. And if we use path compression, it becomes constant. So basically when we call is connected on A and B, it will eventually connect the nodes as to the and make it look like the tree on the right, and then it would become constant. And I suggest for disjoint sets just to put this table on your, or understand it conceptually, but the best idea is to put this on your cheat sheet because that would be really helpful. this is just a summary if you want to refer to it later. And then for sets and maps are some of the most commonly used ADTs. And a set is an unordered set of unique elements. And a map is a set of key value pairs. In Java, set and map are two, they both don't allow duplicate elements and don't maintain insertion order. And the main difference between set and map is that a set is unordered and contains different elements, whereas map contains the data in the key value pair. Okay, so we're gonna move on to binary search trees.
All right, I just clicked this, right? Okay, cool. Let me just make sure. Okay. All right, what's up, guys? My name is Frank. Today we're gonna go over all these trees that you guys have to know about for the next midterm, right? So the first one is gonna be this binary search tree. So just kind of like a quick overview, binary search trees, they're just tree data structures that follow these three properties. The first one is, every node can also serve as the root for a smaller BST. So just a quick example, right? If we select 4 as our root, then that's going to be the root for this entire BST, right? But if we go left and we select 2 as our roots, well, then it's also going to be the root for this smaller BST of size 3, right? With its left child as 1 and its right child as 3. We can keep going. If we select 1 as our root, then it's just going to be a BST of size 1. Same thing with 3. Same thing with 7, or not the same thing with 7, but if we select 7 as our root, then it's going to be a size of 3, the BST. And then, we make 5 our root, it's going to be a size of 1, and so forth with 9, right? Cool. So the second property is going to be every node in the left subtree is going to be less than the root. So what do I mean by this? If we select 4 as our root again, then everything on its left is going to be less than, right? So that means the value of 2, if it goes, let's see, value of 2, it's colored in yellow, is going to be less than 4. The value of 1 is also less than 4, right? And the value of 3 is also less than 4. So all these values in 4's left subtree is going to be less than the root. The same thing goes if we make 2 our root, right? If we make 2 our root, then everything on the left is also going to be less than. So that means the value of 1 is going to be less than 2. And if we make 7 our root, the same thing applies. 5 is going to be less. Cool. And then the last property is everything in the right side is just going to be greater than our root, right? So it's just the opposite of number 2. In this case, once again, if we make 4 our roots, then everything on its right, 7, 5, 6, 7, 5, and 9, that's always going to be greater than the root, right? And then if we make 2 our root, then everything on its right side is also going to be greater than itself. So in this case, it'll be 3. It's going to be greater than 2, right? And then so forth. If we make 7, it's going to be, the 9 is going to be the greater value. Are there any questions regarding BSTs here, or are we good? Okay, seems like we're good, so we'll move on. So the main operation that we'll cover is the BST insertion. Pretty much this follows 2 steps, right? The first one is going to be, we're just going to find the new placement for the node that we're trying to insert. And then the second one is, once we fall off the tree, we just create the node and insert it there. So I'll give you an example, right? Supposedly we have this BST and we want to insert 6 in there. First thing we do is we start from the root, right? And we ask, okay, is 6 greater or less than 4? It's going to be greater than, right? So we go to the right. We hit 7. Is 6 greater than 7 or is it less than 7? It's going to be less than. So we go to the left. And then we hit 5. Is 6 greater or less than 5? It's going to be greater, right? So then we go to the right. But at this point, we fall off the tree. So then we insert the node there because there's no more nodes to traverse. We insert 6. And after that, the BST should be, or, the insertion is just over. And then our height increases by 1 in this BST, right? Cool. So when we analyze the runtime, it's really important that, the order of insertion really determines the height of our BST, right? So what do I mean by this? Well, on the left side, let's insert in the order of 4, and then 2, and then 7, and then we'll do 1, 3, 5, 9. And you can see if we insert in this order, we get like a very bushy tree, right? So what this means is, if we want to find any node, it's going to take at most log n hops. In the worst case, we're going to try to find nodes that are on the leaf, right? The leaf nodes, and pretty much will only take log n hops to get there. But let's say we try to insert in a different order, right? We insert in 1, then 2, and then 3, and then 4, and then 5, 7, 9, so on and so forth. We get this really long spindly tree, right? Oh, whoops. We get this long spindly tree, right? And at this case, our height becomes n, right? So at most, it's going to take n steps to find any type of node, right? If we try to find the leaf node, it's going to take n steps, right? So that's why, it's not so good. It really affects the height of our tree really affects the runtime, right? Cool, that's pretty much this slide, but essentially what we want to really figure out is, is there a way to kind of maintain the height? Because if we can maintain balance or maintain like the most minimum height, then we get a very good runtime out of all our trees, right? Are there any questions regarding this, I guess, or are we Gucci? Okay, I think we're good. Okay, so now we'll talk about balanced search trees, right? So balanced trees, also known as B trees, there's two different types. There's a 2-3 and a 2-3-4 tree. We'll primarily cover 2-3 because it maintains like the 1-on-1 representation of the LLRB that we'll go over next. But basically, a B tree is pretty much like a BST, but just with a slight modification. There's two of them. The first one is nodes can store multiple values now, so not just like one value in there, right? And now non-leaf nodes can have more than 2 children. So to make this more concrete, let's go over an example. On the left side, you'll see the 2-3 tree, right? And the first, or I guess the second thing we said was, non-leaf nodes have 2 or 3 children. So in this case, right, the only non-leaf node is going to be this node with the 3 and the 7. And you can see it's highlighted in red, it has 3 children. For in a 2-3 tree, that's allowed. We'll say, okay, this is cool. The second thing is nodes now can store more than one value, right? In a specific case of 2-3 tree, nodes can store 2 items. So you can see, the root and its 2 left children, they all have 2 items in there, right? The root has 3, 7, its left child has 1, 2, and the middle one has 4 and 6. That's allowed in these B trees, which is not allowed in the BSTs, right? The 2-3-4 tree essentially is going to be the same thing, except we just add 1 to each children and add, for instance, like non-leaf nodes can have up to 4 children now, and each node can now contain more than, or at most 3 items, right? So those are these nodes right here. Yeah, so that's the general graphs of what B trees are, right? Cool. So let's just do a quick insertion of what a B tree actually is, or like the whole process of it. So we insert into the 2-3 tree, it's going to be kind of the same process of a BST, except the only difference is we're actually going to insert into an existing leaf node. So in a BST, we actually just create a new leaf node on its own. But in a B tree, we actually just insert into an existing one, right? So let's walk through this example real quick. If we're trying to insert 5 into this 2-3 tree, well, 5 is going to be inserted into a leaf node, which is going to go into the middle of this, into the middle child, right? After that is done, the second part of the insertion is, okay, we have to check whether nodes violates, if they're overstuffed, for instance. Since we said nodes can only store at most 2 children or 2 items, if we insert an item into a node and it has 3 items, then we need to split the node, right? It becomes overstuffed. So what we do for 2-3 is we actually just, take the middle item and we just break it off and shoot it up into its parent node, kind of like that, right? And then once that's done, well, we see we have 4 children, or the root has 4 children, that's not allowed. But we also see, the root node has also 3 children, or not 3 children, it has 3 items in its node, right? That's not allowed. So once again, we do the same thing. We take the middle item, and then we split it up and shoot it up into to the parent level. In this case, 5 becomes the new root, and then 3 becomes its left child, and 7 becomes its right child. Yeah. Any questions regarding this process? Yeah. Yeah. Yeah, so like 2, 3, 4 trees, or I'll have an example right next. It's like the 2, 3, 4 example. So if we're inserting a 2, 3, 4 tree, right, it's kind of the same thing. We insert into an existing leaf node. So if we're inserting 18 in here, it's going to go, oops, it's going to go into this leaf node right here, right? And then you're asking, okay, do we have to check whether like it's overstuffed, right? In this case, yeah, we still have to check whether it's overstuffed. But instead of taking the middle item, like in the 2, 3, you take the second item from the left. So it's going to be the 17 here, and then you're going to shoot that one up. And then this one's got to check, if it's overstuffed, which once again it is. You take the second element from the left again, which is going to be the 9, right? And then you shoot that one up. So then it's going to look like that. Yeah. So essentially, it's kind of the same process. It's just like 2, 3, 4 trees allow one more element in their node, and they pick kind of like which element you split off kind of differently. So, yeah. Okay, so why do we even care about B trees? Like, what's the big gist, right? Like, who cares about this? Well, B trees, it doesn't matter. If we use B trees, it doesn't matter what type of insertion order we use. Essentially, we're going to get it guarantees perfectly balanced trees, right? So in like the BST example, we had this tree, we're inserting 1, 2, 3, 4, 5, 7, 9, right? We get this really long spindly tree, and we get the worst case scenarios, like we take n hops to get to the leaf node, right? Well, what if we did the same insertion order but in a B tree, right? So we did the same insertion order in the B tree. Let's start at 1. Okay, it's just going to be a leaf node, or I guess it's just the root. Let's insert 2. All right, it goes there. All right, let's insert 3. Once again, it goes into the leaf node. Oh, it's overstuffed. So we got to select the middle node or the middle item and then shoot it up, right? Okay, and then we connect them back into this tree. Yeah. And then let's continue our insert. We go insert 4. Once again, it goes into this leaf node on this right. We insert 5. This right child node becomes overstuffed. So then we shoot 4 back up into its parent, connect 3 as the middle child, 5 as its right child. We do the same thing for the last 2 items, 7 and 9. And then once again, this right child is going to be overstuffed, right? So we select the middle one and we shoot it back up, connect 5 and 9 back to the tree. And then at this point, the root node is also overstuffed. So we break it off again and we shoot it up, right? And then we connect 2 as its left and 7 as its right. But you can see here now, if we have the exact same insertion order, it gives us a perfectly balanced bushy tree, right? Which means now when we try to find any node in this tree, is going to take at most log n hops, right? We avoid this like super crazy long spindly tree on the left, which takes us at most n hops. And we have this, wow, we can insert at any order and we get a perfectly balanced tree, right? It just guarantees, better runtime. Any questions to this? Like why B trees matter? Why would we use them? Okay. All right. So the last thing we'll talk about is pretty much this left-leaning red-black tree. Pretty much in reality, you don't want to use 2, 3, 2, 4, 2, 3, or 2, 3, 4 trees because they're like super hard to code. They're super difficult to implement, right? You have to like split nodes up. You have to keep track whether nodes have multiple values. It's just not fun. So instead, what we use is called this left-leaning red-black tree. And what it is just, it's the same conceptual idea as a 2, 3 tree, but without the complicated, messy code. It's going to be the same structure as the BST, so it's going to be pretty easy to code and implement. But the only difference is we use red links to represent nodes that contain multiple values, right? So on the left here, you see like the 2, 3 tree, and on the right, you see its corresponding representation of an LLRB. So you can think of the LLRB as just, a way to represent the 2, 3 tree, and an easy way to represent the 2, 3 tree with, easy code, right? So in this case, this root node of the 3 in the 2, 3 tree, the root node, it has values 3 and 7, right? But in its LLRB representation, it's going to have this 3 as its left child of 7, and we connect the 2 with a red link. That's all it is, So we just use red links to signify, whether nodes are connected or there's multiple values in a node, right? The same goes with this left child or the node with 1 and 2. 1 becomes the left child of 2 in the LLRB, and it's connected with the left-leaning red link. And same with this middle child here. Any questions regarding this? Okay. Let's see if it moves. Okay, cool. So before we move on, we have to kind of talk about what rotations are. So LLRBs use kind of these rotations to maintain the proper 2-3 tree representation, right? Because essentially we're just using the LRB to maintain this 2-3 structure. So the two type of rotations that you guys are pretty much going to use are just, you rotate left. So when you call rotate left on G, it's going to get a little pedantic, but the more you do it over and over again, it gets kind of easier. But, by definition, if we call rotate left on G, we're going to say, okay, let X be the right child of G. And then all we're going to do is make G the new left child of X, right? So visually, it's going to look like this. If we call rotate left on 1 here, G becomes 1, right? And then we're saying, okay, let the right child of G be X. So what's the right child of 1? It's going to be 3, right? So we label X here on 3. And then when we say, okay, make G the new left child of X, all we're doing is we're going to bring down this 1 node and literally make it the left child of G, right? So after like that animation, you see 1 becomes left child 3, and that's what rotating left is. Rotating right is going to be the same thing, it's just the opposite way, right? So if we call rotate right on G, we're saying, okay, let X be the left child of G, and then make G the new right child of X. So in this case, if we call rotate right on 5, 5 is going to be our G, right? And what's the left child of 5? Is going to be 3. Yeah, so 3 becomes our X. And then we make G the new right child of X, right? So it comes down. Yeah. Yes. Okay, yeah. And then the rotation's finished, right? Okay. Any questions on rotations, or are we good? Yeah. Like in this case, right? Okay, so we called rotate right on 3, then 3 becomes our G, and then the left child of 3 becomes our X, right? So 1 becomes our X, 3 becomes our the G. So then you would scoot, so 1 would take 3's place right now, and then 3 would be the new right child of 1. So then it'd be kind of like like that shape, if that makes sense. So like 3 would be here, 1 would be here, and this would be 5. So it would rotate right like that. That makes sense? Yeah. When in doubt, just, I guess, think of this definition of let X be the left child of G, and then make G the new right child of X, and just label kind of the nodes, which one's G, which one's X, and then just follow along. Yeah. Yeah. Like if I was here, like if you called rotate left on 3. No, not 5 would not, because it's going to be the parent of 3, right? So if we called rotate right on 3, that means G is going to be 3, and then its left child is going to be X. In this case, so this is going to be G, and then this is going to be X, right? So then you're saying, okay, make G this one the new right child of this one. So this one's going to go bam, and this one just goes up. So 5 is not there. It's a little pedantic, right? Like just the more exercise you do over and over again, it kind of becomes like, okay, or like it gets a little more, I don't know, easier. So yeah. You wouldn't be able to rotate 1. I guess you could rotate 1, and then there's a null here. I guess you could, but then you would lose this one because this would be null. So in general, we probably wouldn't do that. Yeah. Good questions. Are there any more? All right, so we'll move on from these rotations. Sorry, there's going to be this laggy animation. Okay, cool. So we have to, LRBs have to maintain this proper balance if they really want to save this like 2-3 tree representation, right? So when you after you insert into an LRB, there's 3 violations you got to be aware of. The first one is the left, it's called the left leaning violation, but essentially it means, there can be no right leaning red links, right? So if we had this 2-3 tree here and we inserted 2, then you can see there's a right leaning red link from 1 to 2, right? That's not allowed. This is called left leaning violation, right? So in order to fix this, what we do is called rotate left on the red link's parent. So it's going to be rotate left on 1. Once again, if that's like we let X be the right child of 1, and then we make 1 the new left child of X, right? So in this case, X is going to be 2. And then we just rotate it like that. 1 becomes the new left child of X. And then the rotation finishes. And you can see we maintain this like left leaning red link, which is what we want. The second violation is going to be incorrect for node. Pretty much, we can't have consecutive left leaning red links, right? Because what this means is like the node is overstuffed. In the 2-3 tree representation, this means this node has 3 values. So when we hit these 2 consecutive left leaning red links, we say, okay, no, we can't do this anymore. So to fix this, we do this rotate right. And we always rotate the top red link's parent, right? So in this case, the top red link parent is going to be this one, right? So we rotate right on 7, and we make 5 the left child of 7, and then we just rotate it. Bam, 7 becomes the new right child of 5, and then we connect it back to the tree, and now we have finished that rotation. And then the third case is, we just have this temporary 4 node violation, which means that nodes cannot have 2 red children. So when a node has 2 red children, this is not allowed. In this case, we have to color flip on the node that has the 2 red children. So in this case, we color flip on 5. What that means is for all of 5's outgoing links, so like 5's links are going to be the ones that are colored here. It has a link to 3 and children 4 and 6. Those just swap colors, right? So after you call color flip on 5, the link to its parent is going to be red, but then its 2 children are going to be black. Yeah. So those are kind of the 3 cases that we run into. Yeah. Yeah, exactly. So like after this rotation happens, there's going to be, it actually violates case number 3, right? There's this node with the value of 5, it has 2 red children. And then because of that, you have to actually call this color flip on it. Yeah, I just didn't put it in there because it's like, I'm trying to break down the 3 different violations. But if you did have like this incorrect 4 node violation, yeah, the color flip would happen after. Like, which to flip? It's just the node that has the 2 red children. Yeah, so all the links that are like outgoing. So like the outgoing links mean like, okay, this one goes, there's one right here, right? And there's one right here. This one's not affected because it's not actually hit inside. So whichever node that has these 2 red children, all of its connecting links here first. Yeah, I thought problem like where like 3 has a red link to 1, and then 3 has a black link to 5, and then so you have to color flip. That would make 3 have 2 red links. Yes, exactly. And then you have to color flip this again. And what would that be? If you color flip this, if these were 2 red links, yeah, this would just be black links. And then, but these aren't affected because they don't connect to it. Then the red links just go away. Yeah, exactly. So it'd just be like a regular gist. Yeah. The root itself, like these nodes don't actually turn red or black. It's just these links. So like, let's say these were all red, right? When you color flip on 3, they would just turn black. But the node itself stays the same color. Because it's only the links that we're talking about. Does that help? Yeah, exactly. There's like, I guess sometimes the problem will be like, use red nodes as like squares or something, and then like black nodes as circles. But I don't really like to follow that. I don't know, like, I think it's a little more confusing. I like to just focus on the links itself. So I don't think you'll actually get like a midterm question that'll be like, okay, use squares as like red nodes and use circles as blacks. But
I'll just point that out. That is like more like a convention thing. Different professors like to do different things, and different like TAs would also do different things. So technically, like when these nodes, like the 4 and 7, are connected with red links, they are sometimes referred to as red nodes. That makes sense? Yeah.
okay, cool. Thank you. All right, any more questions? Good questions. Okay, cool. So I think that takes care of all these 3 cases. I had an example of this insertion, but I think just for the sake of time, I'm just gonna skip it. But if you guys wanted to walk through it, I think you guys have the slides, so you can go through it and just see how everything works. But yeah, we're just inserting 1 and 23, 29 to this LRB. But just for the sake of time, I'm just gonna skip over so we can kind of like go over some like at least a midterm question, and then the other mentors have some time to go over their stuff too, right? Okay. Cool. Once again, these slides are online, so you can just walk through them whenever you get the chance. Okay, so let's just do this quick midterm exercise. Pretty much, we have this LRB like listed above, and we want to draw the resulting tree after inserting 28, 5, and 8. So if you don't have like a red color pen, like what I like to do is, I make the red links like dashes, and then I make the black links just solid lines. That's like an easy way for me to kind of like pinpoint the two. But I'll give you guys kind of like 30 seconds, 45 seconds to, just draw this tree. What does this tree look like after you insert 28, 5, and then 8 in that order? Okay, cool. So just for the sake of time, let's just quickly go over this question, right? So the answer is going to be this. I know it's like that's the final solution, but let's actually kind of like walk through what it actually looks like, right? Like, so at first, if we call insert 28, we just insert like a normal LLRB, right? But all links are going to be red when you first insert. So 28 goes there, right? 28 goes to the right of 24. Does this have any violation? Well, it does, right? It has this temporary for no violation. So we color flip on 24. So what that means is, all of its links, outgoing links, is going to flip. So it's linked to its parent turns red and its children are now black. If we call, or not recall, this insert 28 is not actually done right now because, right, the root has 2 red children. And remember, that's not allowed. That's like the temporary for the violation. So once again, we have to color flip one more time on this, the roots, which means, color flip on 10. Once that happens, all of its outgoing links, so just the left and right child, are going to be black. And then insert 28 is actually finished at this point because there's no actually violation anymore, right? Cool. The next thing is we're going to insert 5. Once again, we always insert as a red link into an LRB. So the 5 goes into the right child of 3. There's another temporary for node violation here, right? So once again, no node can have 2 red children. And in this case, that's going to be color flip on 3, right? So 3 gets color flipped. Bam, it's 2 red, it's 2 children are no longer red, it's black, and its parent link is now red, right? Then now at this point, there's no more violation on this insertion, so this one's done. And then we do this last insert 8, right? Last insert 8, once again, we insert as a left, or we insert as a red link, it's going to be to the left of 9. And then this one actually doesn't have any violations as well, because our links can be left leaning and there's no consecutive left leanings. And then at the result, that's the final solution. Yeah. Any questions to this problem? Yeah. You have to insert one by one. Yeah, you don't insert all at the same time. Yeah, good question though. Anything else? Anyone? Any other questions? Okay, cool. There's more midterm practices, but just for the sake of time, probably won't go through them. But if you guys want to, you guys can take a look at these slides later, go through like the the animations, the walkthroughs, and more practice if you want. But yeah, that will just be the rest of trees. I'm just gonna quickly, go through the slides. Next mentor can take over, do some practice.
All right, good afternoon, everybody. My name is Joseph. Thanks for all coming out today, despite the rain, and hopefully you're all making a decent adjustment to daylight savings. So I'm going to walk you through heaps and priority queues. Right. Okay. So the first thing that we need to talk about is some definitions of what it means for a binary tree to be complete. So that simply means that all the layers of the tree are filled, with the exception of the last layer. And in which case, if the last layer is unfilled, you want all the nodes to be as far to the left as possible. So if you can see on the right-handed tree, we see that there is a missing slot over there, over the bottom left side. So because of that, that tree would be considered incomplete. Now, we can use pictorially a binary tree to describe heaps. And with regards to data structures, we use arrays. So the way this works is that for a given element at some index I, we say that their children would be at indices 2i plus 1 and 2i plus 2, assuming that they exist. So take, for example, the element 3, which is at index 1. We see that its children would be at indices 3 and 4, which match up with what we have up there. And then we look at 5, for example. 5 is at index 3, but there is no index 7 or 8. So 5 is childless. Now, the difference between max heaps and min heaps. So for max heaps, you're just given the structure. The largest element is at the top, and as you work your way down, the elements get smaller and smaller. Min heaps, it'll be just the reverse. Your minimum element is at the top, and they get larger and larger as you go down. Any questions so far on these definitions that I provided? Okay. So we're going to cover two things that we can do with heaps, insertion and deletion. I'm going to do a bit of board work. Do you think it's possible to move the laptop here again? Like, wow. Okay, good, thanks. Okay, so the general procedure for insertion is that we're inserting an element like at the very end of the heap, and then after that, we need to fix the heap. So let's walk through an example to see what exactly that means. So given this array here, elements 10, 5, 3, 2, 4. So the corresponding heap would look something like this. So hopefully you can see from this picture that we are dealing with a max heap here. And let's say we want to insert 12. So the corresponding action for our array for inserting 12 is that we start by inserting 12 at the very end of the array. So I'm going to put the 12 down here, space. And pictorially, it would appear here. So we see right now, this doesn't satisfy the heap property because we clearly know that 12 is much larger than 3. So our first operation to fix this heap is we swap places with 12 and 3. So what does this look like on our list here? Well, here's 12 and here's 3. So again, we move that, 12 and 3. But we still see we need to make one more swap in order for this to finish up. So now we have the 10 down here, the 12 up here. And we flip here. So now this heap property is satisfied, and we have a proper maximum heap, max heap. Now the question comes like, okay, so what's the time complexity of this? So in this case, it's going to be log n. The reason for that being, we have to remember that for binary trees, there are going to be log n levels, where n is the number of elements. And you're going to be making at most like log n different comparisons because you're comparing elements along different levels of the tree. And so since you're like ascending from the bottom to the top, in the worst case, you're going to be ascending log n levels. And so you're going to be making log n comparisons. Questions on that? Okay. So I'm going to, you can try the second example yourself, but for the sake of time, we're going to move on to deletion. So deletion, what you're simply doing is at first you just want to remove the element that you have in question, and then you want to fill up that empty slot with the rightmost element, and then fix the heap again. So let's see what that means. So this example here is a very straightforward 1, 2, 3, 4, 5, 6, and 7. So if I wanted to delete 2, right, get rid of this, I delete 2, and I replace that with the bottommost and rightmost element, which in this case here is 7. So 7 goes here. Now we have here, see here we were working with the min heap. We see that we have a bit of a problem, right? So here, what we want to do is we want to swap 7 with 4. So you're probably wondering, okay, well, earlier we had a 7 up here, we had a 4 and a 5 down here. Why couldn't we have just swapped with 5? Well, the problem is that if you had swapped with 5, right, you would get 5, 7, and 4. You'd still be violating the heap property over here. So that's why we just take a smaller element. And again, with regards to runtime, it's also like have a similar thing where you're making comparisons with different elements and different levels of the tree and working your way from top to bottom. Yeah. Anything? Question, comments, concerns on deletion? No. Okay. So now the punchline. How do heaps relate to priority queues? Well, so you already know what a queue is. And so the different elements of the queues can have priorities. So if you wanted to sort all the elements in a particular order, you can use a heap. And the sorting item, if you will, would just be their priorities. So if you wanted to prioritize things with a higher value priority, then okay, you make a max heap. And the other way around, you make a min heap. Yeah, so. Yeah, any questions on heaps and priority queues and how they are interrelated? All right, if not, time for our last topic.
Okay, choose the arrows. Okay, cool. So today we'll be going over hashing. So yeah, just to get started. Hashing generally refers to a hash table, which is a data structure that allows you to map unique key object value pairs. So what does this look like in terms of an actual visual data structure? You can see that we have those 5 gray boxes on the left-hand side. These are our buckets, which basically store the keys in the form of an integer. And they map to a different object, which will be your value in this case. And that will be a linked list, which will store all of the elements that we want to map to a certain index. So in terms of like hashing and how it actually works, we're going to take a key, which can be like pretty much any element, and we're going to store it in the form of an integer through a hash function. This will then point to a bunch of different values in the form of our linked list. Specifically, our load factor will give us like the average number of elements that will be in each of these linked lists. And the load factor is just the number of items in our hash table divided by the number of buckets that we have. Okay, so what are some of these steps to add items into a hash map or our hash set? We're going to first begin with a key. So we can get a key like a string, for example, like a word. And we have to somehow convert this into an integer, which will give us the index of where we're storing our key. This can be thought of like the index of our hash set. And in order to get this, we're going to first use hash code on our key object. And this is going to return us an integer. Generally, I think Java uses the memory address, which makes it so that way every hash code for any object is unique. But the thing is that we don't have an infinite number of buckets to use. So given the restricted number of buckets, say m buckets, the way that we're going to map every single one of our objects to one of these m buckets is to mod it by the number of buckets. This essentially will give us the integer at which we're going to be storing our object. The next part is to add the key at the index. So we're going to use .equal if the key or object doesn't already exist. And if it does, we're going to do the following. So for a hash map, we're going to update the key with its new value. And for a hash set, we do nothing. So the key difference to make note of here is that hash maps allow you to update the key value object pair. Whereas in a hash set, once you add something to your bucket, there's nothing that can be used to replace it, except like if you remove and then like add it, which is like a couple extra functions, then being able to just simply replace it. Okay, so what makes a good hash code? Obviously, we can just map any key to like another value as an integer just by using like a random function. But this is like a really bad idea. The main reason being that once we add a key to our hash set, we need to be able to look at that same index in order to retrieve those values. So this means that our key or hash code has to be deterministic, as in that whatever key that we put in has to return the same value every single time. And another key property of this is that imagine we have 2 different variables pointing at the same non-primitive object. They should be able to return the same hash code, which means that each equal object should have the same hash code. So now, given we have a hash code, we need to make sure that there's some extra properties that make it a good hash function. The first one is uniformity. Imagine we have like a hash function that maps every value to either the first or the last index. This would be really poor, as now we have just like a bunch of empty buckets and like a long linked list on the first and last values, which basically makes our entire hash set object kind of irrelevant. It doesn't really work out in any way. And the next thing is that it has to be efficient. This means that it should work in like of one time, constant time is what we go by, rather than like anything longer like of n. And the last part is that unequal objects should have different hash codes. So even though different objects will have different hash codes, the same different objects can still map to the same index because we are modding by value. So like, let's say that we have like 2m different values that we're trying to put into our buckets, and we only have m buckets. This will generally and hopefully assign 2 items to each of our buckets. And yet, as noted here, our default hash code will return the memory address. So what does this mean for runtime? In terms of amortized runtime, we can think of our runtime as the load factor actually. Although it says of one here, the fact is that if we have like a certain number of objects, we hope that the number of objects divided by the number of buckets will give us the number of like average elements per item that we're trying to index. Great, thank you. So in the worst case, however, we do have a bad hash function, which means that we're going to be mapping too many objects to single independent values, in which case we literally call into like a certain bucket, and then after that, we're iterating through every single element again, which is O of n time. And for the O of n resize, once we want to expand our load factor, so let's say that we realize that there are too many objects per bucket, we can then make our buckets have less objects per, or have less average number of objects. But in order to do this, we have to reassign every single one of our indices. And this is going to take O of n time because we have to go through each element. Okay, cool. So I guess we only have like a minute or so, but feel free to just quickly work through this question, which is going to be a hashing question. We are given a bunch of elements. We're going to add them to our 4-bucket hash. But once our load factor exceeds 0.75, we're going to have to expand our bucket size. So I'll give you guys a minute to go through this, and then we can just walk through it. Oh, also, if anyone has any questions, feel free to ask them right now. Yeah, go ahead. Yeah, sure. So, in terms of this question, the way that we would find the load factor is that once we've gone above the load factor, so we're trying to add like, let's say a 4th element, or in this case, like, yeah, 4th element, and we only have 4 buckets, we realize that our load factors exceeded it. So at that point, once the 4th element is trying to be added, we have to resize and then reaccount for where all of the indices should go. So as the 3rd element is added, it'll be added normally. Our load factor will be 0.75. But when the 4th element is added, that's when we have to resize. Okay, we can quickly walk through it. So the first thing that's going to happen is that we're going to, let me work through here. So the first thing that happens is that we're going to add 3 based on the way that we find the indices, which is that we take 3 mod 10, which returns 3, and that'll be added to the 3rd index. After that, we add 19, which 19 mod 10 will give us. Oh, interesting. Okay, what's that?
Seems like it's modded by 3.
It's modded by 3. Okay, yeah. So that'll add it to the 1st index. 15 gets added to the 1st index as well. And then at this point, the main important part that we want to work on here is the resize, which is basically going to realize that we're at 0.75. So we're going to double the number of buckets and then reassign all of our values accordingly, which works like this. And then after that, we can add 17 and 18 as such. Cool. Yeah, so that's it for hashing. Go ahead.
Wait, so 19 bucket 1, 15 mod, how to get 9 of this stuff. Like 0, 1, 2, 3.
So 19 mod 10 will give you 9. And then I think it is that you just count 0, 1, 2, 3. I think the hash function in this case. Oh yeah, so you take 19, that gives you basically an integers, which is 9. And then you take that mod 3, and that gives you the value that you're going to be adding the hash function to. or mod 4, sorry, in this case, because there are 4 buckets. Yeah. Yeah. So as we're trying to insert the 10, we have a 4th value added, which means that we've exceeded our, so then we have to resize all of the values, and then we add 10. Mhm. Yeah, so we add the element, then our load factor is 1 essentially, or not our load factor, our like average number of values is 1, which exceeds the load factor. It will not resize. Yeah.
I didn't know to resize if you haven't increased. So like right now our size is 3.
Yeah.
And we haven't exceeded the load factor.
Yeah.
And then we want to insert 10.
Yeah.
But we haven't incremented size, so we don't know if we exceeded the load factor.
So what happens is that we add 10 to our bucket. Our load factor is then recalculated to be 1, and then we call it resize.
Okay, so you first add 10 to the original bucket.
Yeah.
Then increment size.
Yeah.
And then realize it succeeds. Then
Mhm. Exactly. Yeah. And then that will produce like the resize buckets. Okay, cool. If there are no more questions, I'll wrap it up.
All right, thank you, everybody. Once again, slides will be available online, on Ed, so feel free to comment any questions you have under there, and yeah, thank you all for coming. We have a mock exam right now for those interested in, like taking a practice exam. We have 2 other CSM people who are gonna help us out with that. Thank you all for coming.